Hey, good morning, everyone, and good afternoon, good evening, and welcome back. Uh, right now, I am in a somewhat noisy place. If it is too noisy, please let me know. I can make it less noisy if this is disturbing. Um, okay, so traditionally, I seem to start the class by saying, okay, so last time I said something, and there is something else that I should have said. The particular statement for today's lecture or last lecture is a proposition that you see on your screens. Suppose that C is infinite dimensional and countable degree one saturated. Then there are three facts about it. C is non-separable. Every massa is non-separable, and C is not a von Neumann algebra. You may remember that I had some doubts about part number 2 last time. Well, it turns out that the doubts were unfounded. This is actually correct as stated. It's actually quite easy basically. You just define the appropriate type, check that it's consistent, and see that every mass is non-separable. I confused the statement with another statement that looks like negation of part 2, but it's not. So here it is, since it is relevant for what I'll be talking about later on today. So this is an existential statement. There is a countably degree 1 saturated infinite dimensional C-star algebra whose center, Z of C, is separable and infinite dimensional. So just in case you're rusty on algebra, center means all elements that commute with everything else in C. And this is a C-star subalgebra. Right, so I confused, massa is elements that commute with each other, and center is those that commute with everything else. So it is possible to have center which is separable and infinite dimensional. And now what that means in particular is that you can have a countably degree 1 saturated algebra whose center is not countably degree 1 saturated. Which is somewhat curious. It actually it wasn't obvious at all. This follows from standard, very important result that I should mention. It is one of the key properties of the Calkin algebra, and here it is. So it is known as Voiculescu's theorem. What it says is that if you have a separable unital C-star subalgebra of the Calkin algebra, then the following, if you take relative commutant of A in the Calkin algebra, and then take commutant of that, you get A back. So this is true for every separable C-star, yes. For every separable unital C-star subalgebra of the Calkin algebra. There is a related statement, even more important, that predates this von Neumann's commutation, double commutant theorem, which characterizes von Neumann algebras inside all star subalgebras of B of H, but we'll not need that. I'll just tell you that it's an important fact. Now, why I'm mentioning this? Well, okay, so it can be used to prove the previous statement. Well, just take your favorite abelian unital separable infinite dimensional C-star algebra C of X. Think C of 0, 1, for example. That's good enough. Embed it unitally into the Calkin algebra. Right, so it's put a little 1 here. It's important that unit goes to unit, otherwise you get scalars in the commutant no matter what you do. And now take that algebra C to be the relative commutant of the image of C01 inside the Calkin algebra. By Voiculescu's theorem, the center is just C01, which is by choice. separable and infinite dimensional, and therefore we have the result. There is another reason for mentioning Voekulescu's theorem. You see, this is a fundamental property of the Calkin algebra that's used all the time. So I have to admit I couldn't resist quoting from one of my favorite books. So it's by Nate Brown and Taka Ozawa, Seized algebras and finite dimensional approximations. So when they talk about Voekulescu's theorem, they said Voekulescu's theorem is analogous to the Hahn-Banach theorem in two ways. First, it gets used all the time, and it really refers to a collection of related results as corollaries. And in the footnote, they say, thirdly, some authors assume familiarity with all possible formulations and don't bother explaining which version is being invoked. And this is true. I mean, it is funny, but it's actually, it is a true statement. Now, to add to this, you see that they just collected results that they needed. They didn't even bother stating this form of Voekulescu's theorem. And in all honesty, this is actually a corollary. This is weaker than the full Voekulescu's theorem, but it's really the one that is relevant for us here. You see, this is something that should be, I mean, gut feeling is that it should be true in the corona of every sigma unital cyst algebra. Well, it's not, because your corona can be separate. It can be abelian. And if you have an abelian algebra, then of course the commutant of everything is going to be the whole thing. This bicommutant result has no chance of holding there. However, there is actually a conjecture of Gert Pedersen. If C is the corona of a sigma unital cyst algebra and it is simple, you see, by simplicity, you rule out obvious counterexamples. Is it true that every separable unital C-star subalgebra A of C satisfies this bicommutant relation? There are some partial results here. Question is still open. This should have with countable degree one saturation in one way or the other. But I don't have much to say except that this is a nice question. Now, before you start working on this, you should know that simplicity is a fairly rare property of coronas. Early work of Huaxin Lin, he described ideal structure for all sorts of coronas of different algebras, and they typically do have non-trivial ideals. So although there are interesting, important coronas of which are simple themselves, and to take any purely infinite and simple cyst algebra corona is like this, and they're being used a bit. Okay, so let's move on with what I actually wanted to do today. So we move on to the other important class of massive cyst algebras, which is probably even more important than coronas. So let me just remind you, we defined filters in the first class. Here I'm writing J. J is some index set. Really, you lose nothing if you just think of J as the set of natural numbers. You just need an infinite set, and countable is as good as anything for most purposes. So we have a filter on J, and we said it is an ultra filter if it decides for every subset of J. So for every Y subset of J, exactly one of Y and J minus Y belongs to U. This is equivalent to being proper filter and being maximal under inclusion. It's an exercise. So Zorn's lemma proves that every filter, non-principal filter, is included in a non-principal ultra filter. So there is a plenty of non-principal ultra filters on N. I should say what is a principal ultra filter. So it's all Y subset of J, such that some fixed index J belongs to Y. right? So this is an ultra filter, but it's useless. We have no use for it. So really, you want something that is not of this form, and it is a consequence of the axiom of choice that non-principal ultra filters exist. It is still weaker than the axiom of choice, but still it goes beyond ZF. You cannot construct ultra filter in ZF, so that they are set theoretically non-trivial objects. Now here is a lemma which tells us why we care about ultra filters. What is the something that we'll be using all the time. So let's see. So here we are. Here we have our index set J. Here is some compact Hausdorff space X. Think bounded compact interval in real numbers. And there is a function which sends J to X. So lemma claims that there exists a unique point, little x, in big X, which has the property that no matter how you choose open neighborhood V of little x, this pre-image of V belongs to ultra filter for every such V. And moreover, such X is unique. And therefore, we write limit as J approaches to U F of J for such X. Now, just quickly, why is this true? You see, if you look at the set of all V subset of X, which are open, and have the property that the preimage of V belongs to U, and actually you don't want that. You want closures of those sets. This is family of closed sets which has finite intersection property. And therefore its intersection is non-empty. Right, so there is at least one such point. Now, if you had two such points, because space is Hausdorff, you could separate them by open sets whose closures are also disjoint, and you would end up with two disjoint sets, pre-images of those, which are disjoint sets which belong to the ultra filter contradiction. So X exists and it is unique. Now, the sort of intuition here is, okay, so inside compact Hausdorff space, we can, yes. Is somebody asking a question? No. If you have compact Hausdorff space, then you can find this limit. Now, if you're in bounded ball of some infinite dimensional C-star algebra, such limits need not exist. And ultra power is basically a way construction which produces such a limit in such a way that it has all the properties that such a limit is supposed to have. So, we come to definition of ultra products in analysis. Now, if you know some model theory, you know the right definition of ultra power. Here, I'm just stating specialized definition of ultra power of a C-star algebra, and we'll look at slightly more general versions a little bit later on. But I'll try to argue that really it is beneficial to think of this as a special case of a general definition. But anyway, so what is a special case? We have ultra filter on some set J, and we have C-star algebras which are indexed by this index set. So look at this set which I denote by CU. All A, which are in the product, remember this is L infinity product, only bounded sequences of AJs, such that limit of norms of AJs converges to 0. Now, it is an exercise to check that this is a two-sided ideal, which is self-adjoint and norm-closed of the product of all the AJs. And now, once we have such an ideal, we can just look at the quotient product of AJs modulo CU. This is called the ultra product, And here I'm saying norm alpha product because this was the operator norm. Sometimes you might even want to say operator norm alpha product to be very clear what you're talking about. If all the AJs are equal, then alpha product is denoted A sub U and called alpha power. Sometimes people prefer to write a superscript U. In the theory of cyst algebras, there is a reason for writing this because this is well-established notation. A superscript U just means something else. And we'll talk about it, something else a little bit later on. Okay, so in case you haven't seen this, it is definitely a good idea to go over this and to check that this is indeed a non-closed two-sided ideal and therefore self-adjoint. Right? That's a consequence. And here is an exercise that connects this to what we did before. If all AJs are unital cyst algebras, this is important. Then the multiplier algebra of this ideal CU is the product of AJs. And therefore, the alpha product is isomorphic to, actually, it is literally, it is the corona of this ideal. Now, this does not mean that what we said so far applies to alpha products because a CU is never going to be sigma unital, not in the interesting cases anyway. I mean, you just cannot hope to have an alpha filter on an infinite set which is generated by countably many sets. That doesn't happen. So yes, so they are coronas, but they are not coronas of sigma unital cyst algebras. And we have to prove analogous results separately, but we'll see that much stronger results hold in this case. All right, so as I said, this was just a special case of a general definition, and it's my firm belief that to appreciate this definition completely, one has to do a little bit of model theory, at least to get some idea of what is going on. Please bear with me. I guarantee it's worth it. And apologies to logicians that they have to listen to this once again, but hopefully I'm presenting this in a slightly different way. Okay, so there is a famous book by Chang and Kiesler from 1973, I think, which for sufficiently old people like myself was the Bible where to learn model theory from. And basically, the moment you open that book, Chang and Kiesler tell you that model theory is just logic plus universal algebra, which is a true statement. If you're talking about discrete model theory. But that discrete model theory does not apply to cyst algebras or Banach spaces or such. Some, I don't know, 15 years ago, continuous model theory has been developed. Actually, I just realized that I committed a crime of not putting names of founding fathers of continuous model theory on this slide. So it is Ben Yaakov, Berenstein, Hanson, and Osyatsev. Now, this is maybe not quite equality, but to me that they're very close. Continuous model theory is really very close to functional analysis. If you think about it in the way that I think is the right way to think about it. So basically, we'll just be doing slightly different functional analysis to understand alpha products better. So let's go. So first, we need to define terms, but I'll not be defining terms, I'll be cheating. So here is what we have. A is a cyst algebra, just fixed cyst algebra. And actually, what I'm saying, even if A is just the complex numbers, already makes sense, already is interesting enough, but I'll need to know that this makes sense for an arbitrary cyst algebra. Oh yeah, you can ignore this end here. That was from previous incarnation of the slides. We have non-commuting variables. What that means is that if I form a star polynomial in those variables, x times x1 times x2 is not the same as x2 times x1. So you just look at this algebra of polynomials with coefficients in A. So this is an algebra over the complex numbers, right? You can add them, you can multiply them, as scalars. There is one important bit. So you see, we have here infinite supply of variables, but I split them into infinitely many infinite sets by just looking at their indices and insist that for some of those variables, actually each one of those variables is assigned a certain number and it's supposed to range only over the k ball. Really the case when k is equal to 1 is the most important. I mean, even if you just say let all variables range over the unit ball, basically all that I'm going to say is going to be true and make sense, but it's just more natural to think about it this way. All right, so you can think of this as some sort of a graded algebra over A with all these polynomials, right? So if you know that variables belong to k balls, for each polynomial you can compute what ball its range is going to be. So it's really some sort of a grading by natural numbers in this algebra, which has all the natural properties. Now, we move on and take some other East algebra B with proviso that if A is unital, then they better have the same unit because they want unit to mean unit. And take one of these polynomials, this algebra, and look at the evaluation function. So for every tuple B bar, you look at this evaluation of that polynomial. Now, one has to be careful here, and I wasn't careful when I was doing this. So B bar has to be of the appropriate sort. Namely, if x1 is supposed to belong to the one ball, then b1 is in the one ball. If x2 is in whatever ball, then b2 is in that same ball, and so on. So this is really a partial function from certain ball, of B to some other ball of B. Okay, now the elements of this are called terms. There is a more general definition of term, but basically terms are star polynomials. That's if you just remember that, you're not losing much. You're losing something, but not much. We'll eventually expand the language, but this will do. Second part is formulas. So what are formulas? Well, the space is defined recursively. First, the atomic formulas are just expression of the form norm of P of x, where P of x is term, right? So we just compute norm of a star polynomial. Second, if you have n formulas and you have continuous function from r to the n to r, you can just apply a function to those formulas and get a formula. So this already means that formulas also form an algebra. I mean, formulas over A also form an algebra over the real numbers. Now, you may wonder why real, why not complex? Well, that's because we want quantifiers. So if phi is a formula and x is a variable of the appropriate sort to fit into phi, and k is exactly the size of that ball over which x is supposed to be ranging, then inf over norm of x less or equal than k phi and sup norm of x less or equal than k phi are formulas as well. Right, so it's algebra with these two operators on the algebra, and we denote it by f sub a. Correct. Now, still, if A is a subalgebra of B and phi is a formula, then we can define interpretation phi of B from an appropriate sort of B into R. right? So if phi has one free variable and that ranges over 3 ball, then on the 3 ball of B, we define this function. And if you look at these, basically atomic formulas are valued in real numbers, and everything else stays in real numbers. So these are real valued functions on your algebra. Okay. So before we go on to the structure, let's just look at some examples, what can be said by a formula. So first one, just norm of commutator of x, y. Well, the zero set of this formula is exactly a set of pairs of commuting elements. Second, I can quantify out the second variable. Here, as you can see, I'm not being careful about what are the sorts of x and y. It's really going to matter only at one specific place. And here, just if I don't say it, just think of them as belonging to unit ball. That's good enough. Second, sup over all y of norm at most 1 of norm of x, y. Now, zero set of this will be the center, right? All the x's such that everything commutes with them. Third one, well, now you see here I'm quantifying out both x and y. So this formula is just going to have a value. Let's see if I call it phi. Then phi as computed in B is going to be 0 if and only if B is abelian. And it is a little exercise, if you know enough of C-star algebras, that there are actually only two possible values for this formula. If B is abelian, it is 0. And in any other algebra, it has the same value that it has in 2 by 2 matrices, whatever that value might be. I always forget. But basically, this formula has discrete range. So it tells you that abelian or not abelian. Fourth example is not very informative, really, because you see this is just C-star equality. And this is going to be 0 in every C-star algebra. However, this is one of the axioms for C-star algebras, and the right model theoretic setup is to just talk about metric structures in the appropriate language and then axiomatize our theory and talk about models of that. And it has been done. It just turns out we don't really need it. I'm just putting this here to point out that there are non-trivial formulas which are just trivialized because of the structure that we are looking at. Next example. We can expand the language by continuous functional calculus. Now, what do I mean by this? Well, here is a very good example. Exponential function, right? So it is just sum of x to the n over n factorial. This converges no matter where you are on the entire algebra. You don't even need to know that x is normal. So it can be uniformly approximated by polynomial on any bounded ball. And this is where it starts being important, that formulas are sorted. So you see, you know that your x is sorted. It belongs to, I don't know, 3 ball. Now, on that ball, you can approximate x by such and such polynomial up to epsilon you care about. Basically, what that means is that you can just add a new function symbol for the exponential function and just behave as if this was part of the language and allow terms which are not just star polynomials, but also involve exponential function. Okay, if you believe all that, which you shouldn't, you should check everything always. So if you believe all that, then you see that zero set of this formula is going to be what? Well, when is this 0? If our x can be arbitrarily well approximated by exponential of I times some positive element, right? Y star y here is just a typical positive element. So what is the 0 set? Well, it is those unitaries which have logarithm. And now that's where k comes into play. You see, sometimes you have unitary which can be written, which may have a logarithm, but in some case you can choose that positive element to be of norm 2 pi. In some case, you may have to wrap it around the circle a couple of times, and you may need a bigger norm. So depending on how large k is, these formulas really saying different things. Now, before you object and say, wait a minute, this is inf, how do I know that inf is attained? There is a little trick there. If you can approximate unitary, oh, hold on, sorry. No, okay, I take that back. If you can approximate unitary, if it has logarithm, if it is within epsilon of unitary with logarithm, then maybe it still doesn't have logarithm, but it's going to be of the form exp of I times one thing times exp of I times something else. Yeah, okay, so because the only unitaries which don't have logarithm are those that have full circle as the spectrum, and if something is very close to identity, it doesn't have full spectrum. Okay, never mind this. So these are examples of formulas. Now, if you want to prove something for all formulas, the way to go is by induction on the complexity. So I'm just recapping. So again, apologies to logicians here. I'm just recapping it here. So what do you need to prove? You have property P. Well, you prove that all atomic formulas have that property. You prove that if any n tuple of formulas has that property for any continuous functions, when you apply them to phi 0 to phi n minus 1, this has the property again. And finally, same thing for the quantifiers. That's induction on complexity. If you need to define something for all formulas, it's done by recursion on complexity, which is really the same thing. And some people insist that there is no reason to call one recursion, one induction. Maybe they are right, but I just prefer to use separate terms. Okay, so now all this said, if it is clear, let's actually prove something by induction on complexity. Actually, no, first we define something. So you see, this is, if you want to properly define interpretation, then you have to do it by recursion. So phi is the formula over A, and B has A as a subalgebra. B bar is some tuple in B which has the same sort as this, so it fits into phi. You can define interpretation by recursion on complexity. Right, so what your formula looks like, well, it was formed in infinitely many stages. You can define what is interpretation for atomic formulas, just evaluate star polynomial, compute the norm. Then if you have something of this form, apply continuous function. And finally, if you have something of this form, look at soups and infs, search through the appropriate balls, and compute all of these values. So, okay, and yeah, okay. All right. Now, just for definiteness, I'll need to talk about norm on finite powers of my C algebras. I'm just going to look at the maximum norm. Any other reasonable norm would do. So here is important lemma. To every term, or star polynomial if you want, over A, and every formula phi over A, one can associate uniform continuity modules. What do I mean by that? Well, remember, uniform continuity means for every epsilon greater than 0, there exists delta greater than 0. Well, I just call it delta sub phi greater than 0. So basically, this delta or delta sub p, if you're talking about a term, which has the property that it doesn't depend on the algebra B. So whenever you have B, which has A as subalgebra, then if you look at interpretations, this should be P, B, and phi B. If they say that those interpretations satisfy these uniform continuity modules. And moreover, the ranges of P of B and phi of B are bounded subsets of B and of R respectively. Now, this is where we use the fact that all variables are sorted without that proviso. Even if I just had a polynomial, I mean, if I had formula norm of X, the range of this wouldn't be a bounded set. Right? I need to know that X ranges over some bounded ball in order to conclude that this is a bounded set. Now, proof of this is just by induction on the complexity of the formula. Let me just go back to the previous. So basically, for polynomials, you just look at maximum of the norms of coefficients of polynomial. Look at what are the variables, and that's just compute. Sort of, it's a calculus one exercise to find some bounds. You don't need the best bounds. You just need something that's going to work no matter what. Now this is actually a trick. You see, G maps R to N to R to N. It is a continuous function. It's not uniformly continuous. However, the range of each one of these is by induction some bounded interval. So what you have is a continuous function which matters only on some bounded subset of R to the N. So it is uniformly continuous, and therefore you can continue induction. And finally, here, quantifiers actually don't even affect the module's uniform continuity. It just carries from phi to ints and so on.
Are we working in the expanded language?
Doesn't matter. It works. I mean, yeah. You mean expanded by the exponential function?
Yeah.
Oh, it doesn't matter. Yes.
But then, well, the spectrum of each of different normal elements may be different. So,
yeah.
I'll think about it later.
Well, but yeah, okay, you're right. But you see, spectrum is different, but you know the norms. So spectrum is subset of the disk whose radius is the norm of the operator. And you still have uniform, exponential is uniformly continuous on any bounded set. If that's what you meant. I'm not sure that that's what you meant.
But the continuous function you use may not be defined on the whole complex plane, right?
Oh, that's what you meant. Well, that's correct, but they are continuous on the spec. Oh, I see what you mean. Okay, so you're right. One has to be careful how much to expand the language. So definitely you don't want to, I mean, you cannot expand it by some function which is continuous on some obscure set. Right, so I expanded by adding exponential, which is just continuous on the entire complex plane. You expand it by adding something like absolute value or square root or some, right. So you're right, one has to be careful. You expand language by adding reasonable functions that one actually needs. But still, even then, I think, I mean, if you want to have well-defined formulas, you want your new predicate, your new continuous function to have a domain which will include spectra of all the elements that you may want to apply it to, right? Otherwise, your formulas even don't make sense. And if that is the case, it is going to be uniformly continuous with the same modules.
Yeah, actually, I also have another problem. What's the rules about the formation of formulas using those function symbol?
Well, no, you just use function symbols in terms. So I'm just changing definition of term.
Yeah, but you cannot apply it to any term, right? Can you?
Well, to those, well, okay, it depends what functions. Exponential you can, right? Exponential is fine. Absolute value, well, you probably want it to be self-adjoint, but let's not worry about that. So maybe I'm not really going to need expanded language. So basically, Okay, Fanxing has an excellent point. If you're expanding your language, you have to know exactly what you're doing. And I didn't know exactly what I was doing, so that does cause some confusion, perhaps. But really, you know, the formulas that we are going to need are something like absolute value. I don't know, some nth root or such. Or you know, those functions that you've seen before in some continuous functional calculus arguments. You know, function that is at 0, it is 1, and here it's 1 over n, and it's 0 later. You apply it to self-adjoints. So really, we are rather modest when it comes to expanding language. You just expand it with some functions that you actually need in various arguments. And those are typically not very complicated functions anyway. So this is not an issue, but yes, one has to be careful.
Thank you.
Is it okay? Yes. All right. Okay, so here we are. So the fundamental theorem of alpha products, proved by Jerzy Wash back in the 50s, in mid-50s. Now he proved this before ultra powers of C-star algebras have been considered. So he proved it for general discrete model theory, but proof is so general that it works. Here is what it is. If our algebra A is the subalgebra of each AJ for all J in some index set, U is an alpha filter on J, phi is a formula over A, and C denotes the norm alpha power of AJs. Then, to compute phi in A bar for any A bar of the appropriate form in the alpha product, you just compute limit as J approaches to U of phi as computed in AJ of little A bar sub J. You see here, this is my notation, A bar, I have A bar, and here you have representing sequence of it. This is, I'm committing the same crime that is typically committed when one talks about big LP spaces. So, you know, elements of LP space are not functions, they're really equivalence classes of functions, modulo measure 0. Well, same here, elements of alpha product are not elements of the product, but I just choose something and they all work the same. So it's basically, I'm working modulo this ideal C sub U, and it is innocuous abuse of notation, right? But the point here is that to compute formula, you just compute formula at each coordinate, take limit along alpha power, and there you go. And you see, just even to make sense out of this, we need the previous lemma, because our formula phi has modulus uniform continuity. And also we know that in this sort for this variable x bar, the image of phi is contained in some bounded interval inside the reals, and therefore limit along the alpha filter is going to exist. And that limit is exactly the value. Okay, so now this is amazing theorem because everything is in definitions. Proof is you just check it works. Really, the insight was understanding that these are exactly the formulas for which it can be done. So there we go. Case 1. What if our formula is just evaluation of a norm of some polynomial? My computer is informing it it wants to go to sleep. Let me just plug the charger. Okay, so if phi is just norm of polynomial, this is really the definition. The norm, it's really the distance from the ideal, but that's exactly going to be lim sup. But since this is alpha filter, it's really lim. So nothing to prove there. Second case, what if phi is a continuous function of some formulas? If each of these satisfies the conclusion, well, basically, you see, let me see if I want to write this down or not. Okay, so let's write it down. So we have limits as j approaches to u of f of phi 0 to n minus 1. Well, f is a continuous function. Everything is, it's uniformly continuous function. So these really commute. This is just going to be f of limits j approaches to u phi 0, limits as j approaches to u phi n minus 1. And then you just use the inductive assumption and just move limit out of the formula. Finally, the interesting case, the quantifiers. So what is phi is infimum over some k ball of psi, and psi satisfies the conclusion. Well then, first thing to see is that one of the inequalities is immediate. Limit as j approaches to u of the infima is less or equal than infimum of the limit as j approaches to u. So what we want to say, so we just assume that we have limits as j approaches to u of the infimum norm of x less or equal than k. C, this is psi of x, right? It is, let's assume it's equal to some r. And now we use the definition of what does this mean. So it means that the set of all j such that psi as evaluated in aj of xj minus r is less than epsilon, so of course I fix epsilon, 0, that this is less than epsilon, this belongs to the ultra filter. Right, this is how limit is defined. Okay, and now at this step in the proof, we use axiom of choice. So for each one, oh, I think I saw that Daniel was frowning, and I should have known that meant something. I forgot to write something. So y is set of all j such that infimum over norm of x less or equal than k, right? So now it makes sense, I hope. Right, so I'm missing one more absolute value here. Right, so this here, this set belongs to the ultra filter. So for each one of those j's, so for j in y, just fix some xj in aj, which is legit, right? So its norm is less or equal than k, such that psi as computed in aj of xj minus r is less than epsilon. Okay, now y is a set in the ultra filter. Outside of that set, I just define xj's to be whatever. They take them to p0. It just doesn't matter. So just don't waste time on that. And now just look at what is c of x bar. Right, so x bar, actually it's not x bar, it's just x. Just take x to be the sequence xj. So what is psi of x? Well, by the inductive assumption, psi of x as computed in the ultra filter is limit as j approaches to u of psi as computed in aj of xj. And well, that's going to be something very close to r. Right? So since epsilon was arbitrary, I can make this as close to r as I want, and therefore I get the converse inequality here. Right, so that's what it is, right? So this is Walsh's. Oh yes, right. So actually, There's one more case. What about supremum, right? So we have another quantifier, but we don't have to do that really. You can either mimic this proof or just observe that supremum can really be expressed from infimum and everything else, right? So supremum of psi is really minus infimum of minus psi. I never said the formulas for positives. Sometimes that is useful. Here we don't care about that. So basically the last case follows. Basically supremum is definable from the infimum. Okay, so what this tells us is that for example, if property of C-star algebras that you care about at a given moment can be expressed by formulas, then it's preserved by alpha products. So alpha product is abelian if and only if alpha filter many of the algebras are abelian. And there are more interesting properties that can be expressed by formulas, but that's not what I want to do right now. So let's move on. Any questions? Okay. So I want to talk about types, right? So it's really, you know, our next goal is basically extension of countable degree 1 saturation and extension a bit more than that. So remember, F sub A was algebra of formulas over A. It's real algebra, and we can endow it with a semi-norm. So the norm of formula phi of x is the supremum, where here B ranges over all algebras which have A as a unital subalgebra, and B bar ranges over tuples of the appropriate sort in B. So you just evaluate in all of these and take the supremum of all absolute values. This is finite, again, by that lemma that we had before. The range of phi is some bounded interval in the reals. So this is really a Banach algebra norm. It agrees, you know, with addition. You have triangle inequality. You have it's submultiplicative, and it's not Banach algebra because it's not complete. But fine, you can just take quotient and complete and get a Banach algebra. So basically, what we get here is certain formulas are identified with 0, like that formula which just expressed C-star equality. They just vanish. But on the other hand, you get infinitary formulas. If you have, you know, infinite sequence of formulas, you can just basically turn them into convergent series and have formula which is giving you infinite amounts of information. But okay, so we have a Banach algebra, and so starting from fixed A, we produce this Banach algebra M sub A. But what we want to do is relate it with algebras B, which have our A as a subalgebra. Right? So of course, B is a complex, it's C-star algebra. This is a real algebra. Right? They're all real because they want soups and nymphs. Okay, so how do we do that?
Ilijas, you are doing this just for one fixed formula?
No.
So for all formula?
Yes, well, yeah, sure. This is for all 5.
Okay, and then why you say Banach algebra and not topological vector space? I mean, you have semi-norms.
Yeah, but I'm quotienting, so I'm modding out by the kernel. Well, this is norm. This is, you see, look, I think you got it. Elements of my algebra are equivalence classes of formulas.
Ah, okay.
Right?
Yes, okay.
Right, so it is a real Banach algebra. Any questions? I mean, if it wasn't clear to Matteo, I guess it probably wasn't clear to somebody else. So let me know. Okay. So we have this Banach algebra, and here is another definition of a type. Now, I defined degree 1 types before. this is not going to look like the same thing at all, but trust me, it is the same thing. I'm just trying to look at it from different angles, and this is quite a different angle, but very beneficial angle. So here's what we have. We have A, which is subalgebra of C, and now B bar is certain. Okay, so here I wrote infinite sequence. You really care about finite sequence, so I'll just change this n to just a tuple of elements in this C star algebra C. So what is type of B bar? Well, it is the evaluation on this algebra. Now, you see here I have this X bar in a superscript. So those are exactly those formulas which are only in variables which correspond which have the same sort as my B bar. So let's just look at a simple case. If B is a single element in the unit ball, I'm just looking at those formulas which have only one free variable, and that one free variable ranges over the unit ball. That's all I care about. This is actually a subalgebra. You see, if you multiply this formula, if you add them, you don't add new variables. Right? So, so look at this and look at evaluation function from there into the reals. You just evaluate phi into the value of this at C. You don't take absolute value. And then you just check that this actually agrees with multiplication, addition, and everything. So this is a character. Maybe I shouldn't be calling it character, but it is, okay, it's homomorphism from MA into the reals. I'm actually, I have to admit, I'm not sure if this is called character. Typically characters are into complex numbers, but it is unital homomorphism from MA into the reals. And I denoted type of B bar over A in C. Right? Lots of indices. Now, what does type tell you? Well, it tells you everything that you can express with the formula about B, but it tells you a bit more. It tells you, for example, whether B is invertible. You see, you cannot say by a formula whether B is invertible. The naive attempt is to say infimum over all y, such that by minus 1 in norm is equal to 0. But you cannot say that because you need to put some bound on the normal y. And by looking at B, you don't know how much is B bounded away from 0 before you start. So to know whether B is invertible or not, you actually need infinitely many formulas. You need for every case a formula which says there is an inverse of B which has norm at most k. And that is a type. Or to say that B is, for example, if B1 and B2 are two unitaries, to say that they are homotopic, you cannot say by a single formula, and this is also not obvious, but you can say it by a type, because you just need a discrete path so that any two neighboring elements are close enough. If they are close enough, you can connect the dots. So type gives much more information. Basically, it gives you entire first order information of B bar, and even more than that, all first order information with parameters in A. Before I go on, I should say that my use of this A is somewhat non-standard. I'll read it later on. Okay, so we go on. Okay, and here is important definition. Here we have B is a subalgebra of C. We said B is an elementary submodel of C, and write this. If the evaluation of every formula in FB, so you see here I'm taking all of B as this set, but it doesn't really matter what set I'm taking here. Evaluation of every formula in B is the same as that in C. So here is what's going on. Here is B, here is C, and here B1, B2, and whatnot. Now, you see, if you're just talking about star polynomials, quantifier-free formulas, of course, values are the same. But remember, we are taking infima and suprema over bounded balls, and that can make a difference. So what it says is that whether you take imps and sups over bounded balls of B or over bounded balls of C, you get the same values. For example, so this is a stronger than just B being a subalgebra of C. One example, easiest example to see what is the difference, think of B, if B is abelian, sitting inside non-abelian algebra, then the formula inf over norm of y less or equal than 1. This may be 0 in B if you plug B here, but there may be something in C which doesn't commute with B anymore. So it's not an elementary submodel. Okay, and now what does Walsh's theorem tell us? Well, it tells us the following. You see, first, what do I mean here? So I embed A into AU diagonally, just send A into constant representing sequence AAA. This is isomorphic embedding, but what Walsh tells you even more than that is that this is an elementary embedding, because what is value of a formula at A as computed in the ultra power, it is limit as J approaches to U, phi of A, and now here all the AJs are equal the same. This is a constant sequence, right? So it's really the very simple case of Walsh's theorem. So what Walsh's theorem tells us for ultra powers is that ultra power is really a blown up version of original algebra, which still has the same first order properties. It behaves the same in many ways. Now you may wonder why bother then, but of course that's where the other important property of ultra powers comes into play.
Sorry, could
yes.
you go back to the,
Sure.
why can you use a fixed A in the definition?
What do you mean? Well, I need to check this for every A.
Every A?
Yes.
Okay.
Well, sure. I mean, this was accidental, right? So let's put B here, right? So of course, when I'm defining embedding, I'm doing this for all A in A.
I mean the definition, the definition of elementary submodel. Why?
Well, it makes no difference, you see, because A was just providing those constants, right? Basically, if you have FB, any formula phi in FB, what does it look like? Well, you can think of it as phi. Okay, let's say phi x bar. Phi of B bar x bar for B bar. I mean, just collect all those coefficients from B. And put them explicitly put them as values.
Yes, and things in FA are formulas with parameters from A. There are fewer such formulas.
Yes, that's right. There are fewer of them. But you see, these are those formulas, and just look at formula, which instead of those parameters from A has free variables. And just put those parameters in place of those free variables, right? To be elementary submodel, you have to check for every formula, for every possible evaluation of that formula that you have the same value here. And they are just going to show up. Am I answering your question? I'm not sure. It seems that we're talking about different things.
Is this true for discrete model?
Well, yes.
But usually,
I mean, you have expansion. Look, okay, so actually this is a good point. So basically in discrete model, you have B, you have C. So I just expand my language by throwing in constants for a bunch of things here. Well, it's still elementary submodel, right? Because the types of all those constants are the same in B as in C.
Oh,
I'm not,
yeah,
right?
okay, I see what you mean by this definition.
Okay, so I thought you meant something else because I knew that you would know this. So anyway, okay, so is this clear? So if I confuse function, then I probably confuse somebody else. If you're that somebody else, please let me know if it's clear now. Okay, so always have time after the class to discuss if there is any question, or you can email me questions after if you don't want to. Okay, so now we are just back to essentially what we did before with degree 1 types. So let's think of types as sets of conditions. So what is condition? Well, it is, okay, we talk about condition over A. It is expression of the form phi of x is equal to r. Here I should put phi of x bar, right? So it's, here I want to look at types in more than one variable. And the type is just a set of conditions. That's also a direct generalization of degree 1 type. Now, if A is a subalgebra of C, then some type is realized in C if there is B of the appropriate sort, such that every condition in T of X is satisfied by B, which just of course means that if I plug phi of B here and compute this in C, I get exactly R. Right, so that's what it means to be realized. What it means to be approximately realized, well, same as before. For every finite subset of the T, for every epsilon greater than 0, there is B bar, again, of the appropriate sort in C, such that for every condition of this sort, we have that if we compute phi at B bar in C, we end up with an epsilon of R. And such B bar is called the partial realization of T of X bar. Right, so direct generalization of types, degree 1 types as before, except that now our types can have arbitrary polynomials, arbitrary degree, and also involve all sorts of quantifiers and continuous functions, and say a bit more, right? So as I said before, all first order information about something can be coded by these various conditions. Now, how does type as set of conditions relate to type as a functional? Here it is. If A is a subalgebra of C and B is some n tuple in C of that fixed sort, then the kernel of type as a functional is exactly set of all expressions of form phi of x bar minus r, such that B bar satisfies the appropriate condition. Right, so I'm taking advantage here that I can add constants to formulas and subtract and whatnot. So sometimes it is better to think about type as set of conditions, and you can guess it's like before. If you want to check that certain type is realized, we want that. But it is also good to think about types as functionals. Because you have a weak start topology, you have topological methods, and it gives you a more global view of what is going on. But by the way, my favorite trivia here, logicians independently invented weak start topology already in discrete case, but it's called logic topology in logic. All right. So finally, saturation. So we say that the C algebra C is countably saturated if every satisfiable countable type over C is realized in C. So you see, this algebra A disappeared completely. Now, C, which is countably saturated, is going to be large. It's going to be non-separable. So any countable type over C is really going to be countable type over some tiny separable subalgebra of C. So A is going to show up in the context, in the proofs, but it was really an artifact of developing the theory. So what matters here is that we have type, and conditions in a type are allowed to freely refer to two elements of our algebra C. Okay, so countably saturated means that. I should say that there is some, this is actually called countably compact sometimes. I'm slightly sloppy with terminology here. It doesn't matter in our context, but if you read Shallach's classification theory, there are some subtle differences here, but never mind that. Okay, so now what I want to prove is that alpha powers, alpha products are countably saturated. As stated, it's not true, of course. You don't want principal alpha filters, nothing happens. But there is one property of alpha filters that is necessary and sufficient for countable saturation, and here it is, countable incompleteness. So alpha filter is countably incomplete if okay, so actually I should have said on a set J to avoid confusion, because my alpha filter is from set J. So there is a partition of our set J into countably many sets, neither of which belongs to you. This is equivalent to saying that there is a sequence, countable sequence of elements in alpha filter whose intersection is empty. Now, if you have non-principal alpha filter on natural numbers, it is countably incomplete. And if you have a non-principal alpha filter on Aleph 1, it's countably incomplete. And Ulam proved that if you have a countably complete alpha filter, namely one which such that the intersection of any countable elements still belongs to alpha filter, the underlying cardinal would have to be really large. And just a short advertisement break. Those cardinals, minimal cardinal, in which there is such a thing, is called measurable cardinal. You cannot prove that such cardinals exist in ZFC, but if you do have such an alpha filter, you can take alpha power of the entire universe and get a well-founded proper subclass. And from there, you can prove some spectacular things. So for example, you can prove that if you have a Borel subset of R to the third, if you project it to R squared, they complement, project to R again, that is Lebesgue measurable, which you cannot prove if you don't have something like that, which is completely insane. I mean, these are ridiculously large cardinals, but that's some other course. So all that we care about is that any alpha filter that we may encounter here is going to be countably incomplete, and that's really what we want. So really, we don't want our models to be well-founded. So here is the theorem. Suppose that U is countably incomplete alpha filter on some set J, and that AJRC is algebras, then the alpha product, norm alpha product, is countably saturated. Now, this is a relative to Kirchberg's epsilon test. Basically, Kirchberg single-handedly invented quite a bit of model theory. So I should definitely mention that. Okay, so what we need to prove is that in any algebra, any alpha power like this, every countable type which is satisfiable is, which is approximately satisfiable, is satisfiable as well. The template for the proof is what we did in degree 1 case. Actually, it's vice versa. This is much easier proof. What you want to do is take those partial realizations of type and somehow integrate them, put them together to get realization of the entire type. So let's see how it works. First, we fix a type. Right, so here countably many conditions. Now here, this X bar in each of these formulae is the same tuple of variables with same sort. Right, so they all belong to some fixed ball. And now for each n, fix this partial realization. B bar of n. Now B bar of n belongs to this product of AJs. So that for each k less or equal than n, if I compute the value in the ultra filter of one of the first n formulas, it is within 1 over n of what is supposed to be. Now I need to see how to splice these bn's into a single element which witnesses this type. Okay, so by Walsh's theorem, by Walsh's theorem, we know that this condition here, this being less than something, means that there exists a set in our ultra filter such that for every index in that set, approximately the same condition holds. Right? So you see, we moved in one stroke the statement from the entire ultra power to these separate indices, which is exactly what we didn't have in the case of coronas with degree 1 types. There we had to have these approximate units. This is much easier. All right, so what do these sets look like? Well, we have Y1, and you might as well assume that those sets are decreasing, but still in the ultra filter. Now I want to put together something out of these sets. So how do I do that? Well, okay, so I want to define B bar in the product of AJs, which is going to work. Well, how would I do that? Well, on this set here, so on what is this? On Y1 minus Y2, actually, let me write this properly. So I'll do first an attempt, and then we'll see what is the right way to go. So we want B bar sub j to be B bar 1 sub j if j belongs to Y2 minus Y1. Right, so it is, let's take advantage of different colors, right? So this is the green case. Now in the, I don't know, in the blue case, B bar j is going to be B bar 2 of j for j in, okay, I turn this around. So it's Y1 minus Y2. This is Y2 minus Y3, right? And so on. So you want B bar j to be B bar n sub j if j belongs to yn minus yn plus 1. By Walsh's theorem, this will be fine, but my iPad is... So if the intersection of yj's is empty, then for every k, if I compute phi k of B bar in C, it will be limit as j approaches to u, phi k aj of B bar sub j. And now you see, what is this limit? Well, you see these sets are zeroing in. I'm getting closer and closer to the values. It will be exactly what it's supposed to be if the intersection is empty. Okay, but how do I assure that the intersection is empty? Well, just before I do this, just replace my sets with the appropriate sets. So, so to assure that the intersection is empty, replace, let's see, not replace. right? Recall that I have this partition of my set J into countably many pieces, which none of them belongs to the ultra filter. Okay, so let y1 prime be y1 union x1, and then by recursion, yn prime is what? Yn union j less or equal than n of xj's minus the previous yn primes minus union j less than n yj primes. Okay, so I made this look messier than it is, but basically, you see here my sets. So I just add those sets from that partition. There is this partition of J into countably many pieces, all which are small, and I can just keep on adding them to these sets and make sure that that intersection is empty and that in the limit we have the value as required. Is this clear? I can write it once again if it's not clear. I think I did.
Sorry, Ilijas, I don't see why.
Okay.
I mean, why you have the thing with the limit if the intersection is empty? I mean, I see that why you can have.
That you don't see. Oh, I see. Well, you see, if the intersection is empty, let's okay. So let's go back to that. Okay. So what is limit? Okay. So here we have this B bar that I defined here, right? So you want to see what is. Okay, so I fix K in M, right? So I look at what is phi K in the ultra product of AJs of B bar. Okay, so it is limit as J approaches to U, phi K in AJ of B bar sub J. But now what is this limit going to be? So look, limit as J approaches to U of any sequence Sj is equal to some Rk if and only if for every epsilon greater than 0, the set of those J's such that Sj, actually I shouldn't have called this Rk, I called it Rk for obvious reasons, but it's not going anywhere. This difference is less than epsilon. This set belongs to the ultra filter. And that is what I assured, right? You see, because if my epsilon is 1 over 3, that set is subset of this set here.
So I think the point of empty intersection is that you can define the tuple B. You can define B bar.
Exactly. Yes, of course. Right. Sure. Of course. Yes, exactly. So this wouldn't be a definition. That's correct. That's correct. Yes. Right. I wouldn't know what to do on the intersection otherwise. And that's exactly what I said. Thank you. That's exactly what I said before. You see, these BJs along a bounded ball of C star algebras, they are not going anywhere. So there is no limit because you don't have compactness. So if this intersection is non-empty, you just have some sequence of elements that are satisfying your type better and better, but they're not converging to anything. So you cannot define a limit. Yes, thank you. That's a good point. Okay, so how are we? Okay, so I'm almost out of time, but I just have to wrap this up. So it's not going to make sense if I yes. Question?
So if you're adding a set X to your Y1, right? You're unioning something. How do you guarantee that for every J in that new bigger set, you have the same condition as before?
I'm removing the previous ones. So, okay, so I should have, no. What am I saying? What am I saying? Sorry. No, you're right. No, I shouldn't have said that.
Well, actually, you just mentioned that countability incompleteness is equivalent to you have a decreasing sequence which has empty intersection, and you intersect Y with that sequence.
That is correct. Thank you. So yes, so I just made this messier than it should have been. So okay, so let's say that Zj is union J greater or equal than N greater or equal than J of my Xn's, right? So each one of these belongs to the alpha filter. Yeah, thanks function. So what I exactly, so my Yj prime is just Yj intersected with Zj. Yeah, thanks. Yeah, I just made it ridiculously complicated. Right, so now it makes sense. Yeah, I know, just with these Boolean combinations, it's messy. Okay,
Yeah,
so
but I have
let's.
a question.
Yes.
But it's
Yes.
not really important that you fix on a finite tuple for the type. You could have also a countable tuple, and it would work. This
Yeah.
proof.
Oh, yeah, that's correct. And that's useful. That's correct. Sure. Thank you. Right. So you have countable types. Yeah. Okay. So corollary. Now, if U is a non-principal alpha filter and this is algebras, C is alpha product, and B is a separable subalgebra of C, then each one of C and relative commutant of B inside C is countable degree of unsaturated. Therefore, it has all the properties that we proved for countable degree of unsaturation before. We get it for free, right? So boundary representations for amenable groups, countable, amenable. I forgot to say countable. Are uniformizable. You have this discontinuous functional calculus. Alpha power is never going to be tensor product of two infinite dimensional East algebras, no matter what tensor product you're taking, and so on and so on. But we actually get more because we have not just degree one saturation. Remember, there were some statements that we could not express in degree one way, like something being a unitary, but something being a unitary is expressed by degree two condition. You just need to say that x star is equal to 1, that x star x is equal to 1. It's just a tiny bit, but now we can do that as well. So there are tons and tons of other consequences. I just wanted to say important one for the end, proved by F.S. Rosenberg and another one by Kirchberg. For every separable East algebra B, the following are equivalent. First is finitary statement. For every finite subset of B, for every epsilon less than 0, there is an embedding of 2 by 2 matrices into B so that it epsilon commutes with all elements of F. What I mean by that, I mean that matrix units of M2 of C epsilon commute, right? So elements of big norm are not going to epsilon commute anymore. You see, this here just tells you that certain type is consistent. You can write down the type, right? So type says that basically type over the entire algebra. That no matter how you pick finite many elements, there's going to be something that looks like matrix units of M2, and you can describe that by a formula that's consistent. And then what that means, well, because alpha power is countably saturated, that means that 2 by 2 matrices embed into the alpha product, and even in such a way that they sit in the commutant. Okay, but now there is a little trick. You can go back and code finite subsets of this type by formulas, and with a little bit of an exercise here, prove that means that 2 by 2 matrices embed into relative commutant of any separable subalgebra of the alpha power. So in particular, you can just generate subalgebra by B and first copy of 2 by 2 matrices. Right, so here we are. So here is the algebra power. Here is B. So here you get one copy of 2 by 2 matrices. Then you get another commuting copy, another one, and so on, and get the entire car algebra to embed here. Here one has to say something that this is nuclear. This actually has only one meaning. The tensor product is well defined for these matrices. But you see, even after countably many steps, you're still separable. You can go on. So you can embed tensor product of Aleph 1 copies of 2 by 2 matrices into relative commutant. And there is more. This is not just about matrix algebras 2 by 2 or 3 by 3 or any other. Analogous statement when M2 of C is replaced by some separable subalgebra D. The only statement you need to modify is the first one. Here I had the entire thing embeds into B. If you have some separable subalgebra, you just want to say that any finite subset of D approximately embeds with appropriate multiplication and addition table into there, and you still have equivalences. Right, so these are statements that are being useful, being proved all the time. Okay, so I almost went over time. I should stop here. Thank you. Any questions? Okay, I guess everybody. Oh yes. Would you mind repeating a bit about taking a fixed? Oh yes. Oh yes. Right. So actually, I can just say it once again. Yeah. So what I'm planning. So I'm going to move on to standard model theoretic. I mean, this is not question about C algebras, although it makes sense. So here we have B and we have C, and assumption is that B is an elementary subalgebra of C, and it is elementary with respect to F subcomplex numbers, right? Basically, complex numbers mean empty set for me, right? We have constants for all complex numbers. So what I claim here, oh yes, thanks. What I claim here is that if you expand the language, so if you pick subalgebra A of B, it doesn't have to be elementary. It doesn't even have to be a subalgebra. I'm just saying we are expanding language by throwing in a bunch of constants. So really, I mean, I just need to prove that I can add one constant. Let's do that, and it's going to be clear. So just you have some element A here. So what I claim is that I can look at the language. Now, this is not a subalgebra, but what I mean by F sub A, I just mean I'm allowing formulas which have a constant for this distinguished element A. Well, the point here is that type of A in B, and I'm talking about type over empty set, is equal to type of A. Oops, this is not complex numbers, this is C. Right, but by elementarity. So any formula in which constant A occurs, right? If I have formula X bar and constant A as computed in B, it will be equivalent or equal. The value is equal to this as computed in C, because the assumption was that if I looked at this other formula, right, so I'm just looking at formula from which phi was obtained. Here, y is a variable of the appropriate type. The assumption was that this value and this value were the same, right? So there is no difference, right? So it's just a basic. You see, this algebra A is an artifact of the way that I wanted to present everything. It was just easier to talk about it this way. For some reason, my iPad is getting stuck every now and then. Talk about it this way, than to start talking about language and then expanding by adding constants and yada, yada, yada. I just fix a subalgebra and it works. Note, by the way,
did you say that?
Yes.
Did you just say that a complex number is the same as empty set?
Well, yeah, we have constants for, if we are talking about unital C algebras,
Yeah.
right? So if A is unital, then I just identify all the scalars with complex numbers. So I think of complex numbers as a unital subalgebra of A. And the scalars are there. You have constants for those. As long as you're insisting of having only unital embeddings, of course. If you have non-unital embedding, then scalars change their meanings. So that's something else.
Why do I have constant symbols for complex numbers?
Are you complaining about having constant symbols for complex numbers?
Is that part of the definition? I mean, what if you don't? What if you don't allow any parameters?
Well, okay. So one context in which you definitely want to have complex numbers. You see, for every lambda in C, there is a formula which is multiplication by that scalar lambda. And what is this really? Basically, actually, no. I mean, if you don't allow complex numbers, nothing makes sense, because the way I define terms, remember, my terms were star polynomials over A. If I have empty set, star polynomials over empty set, that's empty set, right? So I definitely want at least star polynomials over complex numbers. So it's again artifact of the presentation. But any two reasonable presentations are equivalent. So it really makes no difference here. Welcome. Okay, so any other questions? Okay, so I'm available basically. I'll see you on Friday, but in the meantime, if you have any questions, please feel free to email me. And yeah, so next time we'll continue with more about saturation. Okay, thanks, and have a great day, everybody. Bye.